If you got a function f of x, you know the value at some point, and you want to go to a neighboring point, a distance delta x away, you ask how much does the function change? And the answer is the change in the function delta f is the derivative of the function at the starting point times the distance you move. This is not an equality unless f happens to be a straight line. It's an approximation, and there are corrections to this. That's what all the dots mean. Corrections are proportional to delta x squared and delta x cubed and so on, but if delta x is tiny, this will do. That's it. But today, we are going to move the whole work energy theorem and the law of conservation of energy to 2 dimensions. So when you go to 2 dimensions, you got to ask yourself, what am I looking for? Well, in the end, I'm hoping I will get some relation like k1 plus u1 is k2 plus u2, assuming there is no friction. u2 is going to be my new potential energy. Then if it's a potential energy and the particle is moving in 2 dimensions, it's got to be a function of 2 variables, x and y. So I have to make sure that you guys know enough about functions of more than 1 variable. So this is again crash course on reminding you of the main points. There are not that many. By the time I get here, I'll be done. So how do you visualize the function of 2 variables? Function of 1 variable, you know, you plot x this way and the function along y. If it's 2 variables, you plot x here and y here, and the function itself is shown by drawing some surface on top of the xy plane, so that if you take a point and you go right up till you hit the surface, that's the value of the function at that point xy. It's like a canopy on top of the xy plane, and how high you got to go is the function. For example, starting with the floor, I can ask how high do I have to go till I hit the ceiling. That function varies. There are dents and dimples and so on, so the function varies with xy. Another example of a function of x and y could be coordinates in the United States, and the function could be the temperature at that point. So you plot it on top of that. Each point, you plot the temperature at that point. So once you got the notion of a function of 2 variables, if you're going to do calculus, the next thing is, what about the derivatives of the function? How does it change? Well, in the old days, it was dependent on x, and I changed the x, and I found the change in the function divided by the change in x and took the limit, and that became my derivative. But now I'm sitting in the xy plane, so here is x and here is y. I'm here, the function is coming out of the blackboard. So imagine something measured out, but I'm sitting here. Now I want to move and ask how the function changes. But now I have a lot of options. In fact, I have an infinite number of options. I can move along x, I can move along y, I can move at some intermediate angle. So you have to ask, what do you want me to do when it comes to time to take derivatives? So it turns out, and you will see it proven amply as we go along, that you just have to think about derivatives on 2 principal directions, which I will choose to be x and y. So we're going to define one derivative, which is defined as follows. You start at the point xy, you go to the point x plus delta x, same y, and subtract the function at the starting point, divide by delta x, and take all the limits. Delta x goes to 0. That means you go from here to here. You move a distance delta x, you find the change in the function, you take the derivative. As you move horizontally, you notice you don't do anything to y. Y will be left fixed at whatever y you had. X will be changed by delta x. You find the change, you take the derivative and take the limit. That is denoted by the symbol df dx. So this curly d instead of the straight d is to tell you it's called a partial derivative. Some people may want to make it very explicit by saying this is the derivative with subscript y. That means y is being held constant when x is varied. But we don't have to write that because we know we got 2 coordinates. So if I'm changing one, the other guy is y. So we won't write that. That's the partial derivative. So you can also move from here to here, up and down, and see how the function changes. So I won't write the details, you can define obviously a df dy. So one tells you how the function changes with x as you move along x. Other tells you how it changes with y as you move along y. So let's get some practice. So I'm going to write some function, f equals x cubed y squared. That's a function of x and y. You can write any, let's make it a little more interesting, plus y, or y squared. That's some function of x and y. So when I say df dx, the rule is find out how it varies with x, keeping y constant. That means really treat it like a constant. If it was number 5, what will you do? If y was equal to 5, this will be 25, and it's not part of taking derivatives because it's not changing. And here, it will be just standing in front doing nothing. We'll just take the x derivative, treating y as a constant. You're supposed to do that here. This is a derivative 3x squared y. So that's the x derivative. Now you can take the y part, y squared. Yes, thank you. Then I can take df dy. So then I look for y changes. This is 2y here. So it's 2x cubed y plus 2y. So that's the x derivative and the partial y derivative. Okay, so then you can now take higher derivatives. We know that from calculus of one variable, you can take the derivative of the derivative. So one thing you can think about is d2f dx squared. That really means take the d by dx off the d by dx. That's what it means. First take a derivative and take the derivative off the derivative. So let's see what I get here. I already took df dx. I want to take its derivative, right? Derivative of x squared is 2x. So I get 6xy squared. Then I can take the y derivative of the y derivative, d2f dy squared. That's d by dy of df dy. If you take the y derivative there, you guys should keep an eye out for me. When I do this, I get this. But now we have an interesting possibility you didn't have in one dimension, which is to take the x derivative off the y derivative. So I want to take d by dx off df dy. That is written as d2f dx dy. Let's see what I get. So I want the x derivative off the y derivative. So I go to this guy and take its x derivative. I get 3x squared from there. So I get 6x squared y, and that's it. So make sure that I got the proper x derivative of this. I think that's fine. Then I can also take d2f dy dx. That means take the y derivative of the x derivative. Well, here's the x derivative. Take the y derivative of that, put a 2y there, and I get 6x squared y. So you're supposed to notice something. If you already know this, you're not surprised. If you have never seen this before, you will notice that the cross derivative, y followed by x and x followed by y, come up being equal. That's a general property of any reasonable function. By reasonable, I mean you cannot call the mathematicians to your help because they will always find something where this won't work. Okay, but if you write down any function that you are capable of writing down with powers of x and powers of y and sines and cosines, it will always be true that you can take the cross derivatives in either order. You get the same answer. Now, I'd like to give you a little bit of a feeling for why that is true. It's true, but it's helpful to know why it's true. So let's ask the following question. Let's take a function and let's ask how much the function changes when I go from some point x, y, to another point x plus delta x, y plus delta y. I want to find the change in the function. So I'm asking you, what is f of x plus delta x y plus delta y minus f of xy for small values of delta x and delta y. If the neighboring points, what's the change? So we're going to do it in two stages. We introduce an intermediate point here whose coordinate is x plus delta x and y. And I'm going to add and subtract the value of the function here. Adding and subtracting is free, it doesn't cost anything, so let's do that. Then what do I get? I get f of x plus delta x, y plus delta y, minus f of x plus delta x, y, plus f of x plus delta x, comma y, minus f of xy. I'm just saying the change of that guy minus this guy is the same as that minus this plus this minus that. That's a trivial substitution. But I write it this way because I look at the first entity here. It looks like I'm just changing y. I'm not changing x. You agree? So what will this be? This is going to be the rate of change of the function with respect to x times delta x. And this, I'm sorry, I got it wrong, with respect to y times delta y. This one is df dx times delta x. Therefore, change in the function, if I add it all up, I get df dx delta x plus df dy delta y. But if you're pedantic, you will notice there's something I have to be a little careful about. What do you think I'm referring to in my notation? Yes? Meaning? But this is nothing to do with dimension. You see, it's one number minus another number. I put another number in between. And in this function, it's a function only of here. Let me see. X is not changing at all and y is changing, so it is df dy delta y. I meant something else. So that is, in fact, a good approximation, but there is one thing you should be careful about, which has to do with where the derivatives are really taken. For the term here, x plus delta x minus y minus f of xy, I took the derivative at my starting point. If you want, I will say it's at the starting point xy. In the second one, when I came here and I want to move up, I'm taking the derivative with respect to y at the new point. The new point is at x plus delta x, comma y. So derivatives are not quite taken at the same point. So you got to fix that. And how do you fix that part? You argue that, well, the derivative with respect to y is just another function of y, right? F is a function of y, its derivatives are functions of x and y, everything is a function of x and y. And we are saying this derivative has been computed at x plus delta x instead of x. So it is going to be df dy at xy plus d2f dx dy times a delta x. In other words, I'm saying the derivative at this location is the derivative at that location plus the rate of change of the derivative times the change in x. In other words, the derivative itself is changing. So if you put that together, you find it is df dx delta x plus df dy delta y, where if I don't put any bars at anything, it means at the starting point xy, plus d2f dx dy delta x, delta y. Now you got to realize that when you're doing these calculus problems, delta x is a tiny number, delta y is a tiny number. Delta x, delta y is tiny times tiny. So normally we don't care about it, or we don't. If you want to be more accurate, of course, you should keep that term. So in the first approximation, where you work to the first part of everything, this will be your delta f. But if you're a little more ambitious, where you keep track of the fact that the derivative itself is changing, you will keep that term. But another person comes along and says, you know what, I want to go like this. I want to introduce as my new point, intermediate point, the one here. It had a different value of y in the same x, and then I went horizontally. Then I keep track of the changes. What do you think that person will calculate for the change in the function? That person will get exactly this part, but the extra term that person will get will look like d2f dy dx times delta y delta x. If you just do the whole thing in your head, you can see that I'm just exchanging the x and y roles. So everything that happened with x and y here will come backwards with y and x. But then the change between these 2 points is the change between these 2 points. And it doesn't matter whether I introduce an intermediate point here or an intermediate point there. Therefore, these changes have to be equal. This part of it's of course equal. Therefore, you want that part to be equal. Delta x delta y is clearly delta y delta x. Then the consequence of that is d2f dx dy is equal to d2f dy dx. That's the reason it turns out when you take cross derivatives, you get the same answer. It comes from the fact, if you say, where is that result coming from? It comes from the fact, if you start at some point and you go to another point and you ask for the change of the function, the change is accumulating as you move. You can move horizontally and then vertically, or you can move vertically and then horizontally. The change of the function is a change of the function. You've got to get the same answer both ways. That's the reason, that's the requirement that leads to this requirement. Now, I will not be keeping track of functions to this accuracy. In everything we do today, we'll be keeping the leading powers in delta x and delta y. So you should bear in mind that if you make a movement in the xy plane, which is delta x horizontally and delta y vertically, then the change in the function is this. We draw a box around that because that's going to be, this is just the naive generalization to 2 dimensions of what you know in 1 dimension. You are saying, look, the function is changing because the independent variables x and y are changing, and the change in the function is one part which I blame on the changing x and a second part which I blame on the changing y, and I add them. So you're worried about the fact that we are moving in the plane and there are vectors. That's all correct. But f is not a vector. F is just a number, and its change has got 2 parts. Okay, so this is the basically all the math we will need to do what I want to do today. So let's now go back to our original goal, which was to derive something like the law of conservation of energy in 2 dimensions instead of 1. So you remember what I did last time, so I will remind you one more time what the trick was. We found out that the change in the kinetic energy of some object is equal to the work done by a force, which was some F times delta x. And then if you add all the changes over a not infinitesimal displacement, but a macroscopic displacement, that was given by F times dx. And the F times dx from x1 to x2, if f is a function only of x, from the rules of calculus, can be written as a difference of a function at this limit minus that limit, and that was u of x1 minus u of x2, where u is that function whose derivative with a minus sign is f. That's what we did. Then it's very simple now to take the u1 to the left-hand side. Let me see. K1 to the right-hand side and ux2 to the left-hand side to get K2 plus U2 is K1 plus U1, and that's conservation of energy. You want to try the same thing in 2 dimensions. That's your goal. So first question is, what should I use for the work done? What expression should I use for the work done in 2 dimensions? Because the force now is a vector. Force is not one number. It's got an x part and a y part. My displacement has also got an x part and a y part, and I can worry about what I should use. So I'm going to deduce the quantity I want to use for delta W, namely the tiny work done, which is an extension of this. I'm going to demand that since I'm looking for a work energy theorem, I'm going to demand that, remember in one dimension, delta K is F delta X. If you divide by the time over which this happens, I find dk dt is equal to force times velocity. I'm going to demand that that's the power. Force times velocity is what I call the power. I'm going to look for dk dt in 2 dimensions of a body that's moving. What's the rate at which kinetic energy is changing when a body is moving? For that, I need a formula for kinetic energy. Formula for kinetic energy is going to be, again, 1/2 mv squared. I want that to be the same entity, so I will choose it to be that. But v squared has got now vx squared plus vy squared, because you know whenever you take a vector v, then its length is the square root of the x part squared plus the y part squared. Any questions? Okay, so let's take the rate of change of this, dk dt. Again, you have to know your calculus. What's the time derivative of vx squared? Then the rule from calculus says, first take the derivative of vx squared with respect to vx, which is 2vx, then take the derivative of vx with respect to time. So you do the same thing for the second term, 2vy dvy dt, and that gives me, the 2's cancel, gives me m dvx dt times vx plus m dvy dt times vy. This is the rate at which the kinetic energy of a body is changing. So what's my next step? Yes?
Wait, what happened to the half?
The half got cancelled by the 2 here. Yes?
Taking the mdv and converting to acceleration is dv, or mdv is force because dv.
That's correct. So what we want to do is to recognize this as ma in the x direction, because m times dv dt, dvx dt is ax, and this m times ay, therefore they are the forces in the x and y directions. So I write fx vx plus fy vy. So the power, when you go to 2 dimensions, not very different from 1 dimension. In 1 dimension, you had only one force and you had only one velocity. In 2 dimensions, you got an x and y component for each one, and it becomes this. So this is what I will define to be the power. When a body is moving and a force is acting on it, the force has 2 components, the velocity has 2 components. This combination shall be called power. But now, let's multiply both sides by delta t and write the change in kinetic energy is equal to fx. Now you guys think about what happens when I multiply vx by delta t. Vx is dx dt. Multiplying by delta t just gives me the distance traveled in the x direction plus fy times dy. So this is the tiny amount of work done by a force, and it generalizes what we had here. Work done is force times delta x. In 2 dimensions is fx dx plus fy dy. It's not hard to guess that, but the beauty is this combination. Now you can say, you know what, I didn't have to do all this. I could have always guessed that in 2 dimensions, when you had an x and a y, you obviously got to add them. There's nothing very obvious about it, because this combination is now guaranteed to have the property that if I call this the work done, then it has the advantage that the work done is in fact the change in kinetic energy. So I want to define work so that its effect on kinetic energy is the same as in 1D, namely work done should be equal to change in kinetic energy, and I engineered that by taking the change in kinetic energy, seeing whatever it came out to, and calling that the work done. So I cannot go wrong. But now we notice something repeating itself all the time. which is that I had a vector f, which I can write as I times fx plus j times fy. I had a vector velocity, which is I times vx plus j times vy. Then I had a tiny distance moved by the particle, which is I times dx plus j times dy. So the particle moves from one point to another point. The vector describing its location changes by this tiny vector. It is just the step in the x direction times I plus step in the y direction times j. So what you're finding is the following combination. The x component of f times the x component of v plus the y component of f times the y component of v. Or f component of x times the distance moved in x plus y component of f times the displacement in y. So we are running into the following combination. We are saying there seem to be in all these problems two vectors, I times ax plus j times ay. A, for example, could be the force that I'm talking about. There's another vector b, which is I times bx plus j times by. Right? For example, this guy could be standing in for f, this could be standing in for v. The combination that seems to appear very naturally is the combination ax bx plus ay by. It appears too many times, so I take it seriously. Give that a name. That name will be called the dot product of a with b, and it's written like this. Whenever something appears all the time, you give it a name. This is a dot b. So for any two vectors a and b, that will be the definition of a dot b. Then the work done by a force f that displaces a particle by a tiny vector dr is f dot dr. The particle is moving in the xy plane. From one instant to the next, it can move from here to there. That little guy is dr. It's got a little bit horizontal and it's got a little bit vertical. That's how you build dr. The force itself is some force which at that point need not point in the direction in which you're moving. It's some direction. At each point, the force could have whatever value it likes. So the dot product, sometimes you learn the dot product as ax bx plus ay by. You can ask, who thought about it? Why is it a natural quantity? So here is one way you can understand why somebody would think of this particular combination. So once you got the dot product, you got to get a feeling for what it is. First thing we realize is that if you take a dot product of a with itself, then it's ax plus ay, which is ax squared plus ay squared, which is the length of the vector a, which you can either denote this way or just write it without an arrow. So a dot a is a positive number that measures the length squared of the vector a. Likewise, b dot b. Now we have to ask ourselves, what is a dot b? So somebody know what a dot b is? Yep. Okay, so how do we know that? How do we know it's length of a times length of b times cosine of the angle? It should follow from, is it an independent definition or is it a consequence of this? Yep.
Or you can derive it using the law of cosines.
Yes. He said we can derive it using the law of cosines, and that's what I will do now. In other words, that definition, which you may have learnt about first, is not independent of this definition. It's a consequence of this definition. So let's see why that's true. So let's draw two vectors here. Here is a, and here is b. It's got a length a, it's got a length b. This makes an angle theta sub a with the x-axis, and that makes an angle theta sub b with the x-axis. Now, do you guys agree that the x component of a, which is the horizontal part of a, is a cosine theta times a? You must have seen a lot of examples of that when you did all the force calculation. And ay is equal to the length of a times sine theta sub a And likewise for B, I don't feel like writing it. If you do that, then A dot B will be length of A, length of B times cosine of theta times A, cosine of theta times B, plus sine theta A, sine theta B. Now you got to go back to your good old trig, and it'll tell you this cos plus sine is cos of theta A minus theta B. So you find it is length of A, length of B, cosine of theta A minus theta B. Often people simply say that is AB cosine theta, where it's understood that theta is the angle between the two vectors. So the dot product that you learned, I don't know which way it was introduced to you first, but these are two equivalent definitions of the dot product. In one of them, if you're thinking more in terms of the components of A, a pair of numbers for A and a pair of numbers for B, this definition of the dot product is very nice. If you're thinking of them as two little arrows pointing in different directions, then the other definition, in which the lengths and the angle between them appears, that's more natural, but numerically they are equal. An important property of the dot product, which you can check either way, is the dot product of A with B plus C is dot product of A with B plus dot product of A with C. That just means you can open out the brackets with dot products as you can with ordinary products. Now that's a very important property of the dot product. So maybe I can ask somebody, do you know one property, significant property of the dot product?
When two vectors are perpendicular, their dot product equals to 0.
Oh, okay, that's an interesting, I didn't think about it. Yes, one thing is if two vectors are perpendicular, the dot product is 0 because cosine of 90 is 0. But what I had in mind, of course, it's hard for me, it's not fair I ask you some question without saying what I'm looking for. What can you say if you use a different set of axes? Yep.
It doesn't matter, it's invariant.
If you go to rotated axes, the components of the vector A will change. We have done that in the homework, we've done that in the class. Components of B will also change. Everything will get a prime. But the combination AX, BX plus AY, BY, when evaluated before or after, will give the same answer. Because it's not so obvious when you write it this way. But it's very obvious when you write it this way, because it's clear to us if you stand on your head or you rotate the whole axis, what you're looking for is the length of A, which certainly doesn't change on your orientation, or the length of B, or the angle between them. The angle theta A will change, but the angle with the new x-axis won't be the same. Angle with the new y-axis won't be the same, likewise for B. But the angle between the vectors, which is an invariant property, something intrinsic to the two vectors, doesn't change. The dot product is an invariant. This is a very important notion. When you learn relativity, you will find you have one observer saying something, another observer saying something. They will disagree on a lot of things, but there are a few things they will all agree on. Those few things will be the analog of A dot B. So it's very good to have this part of it very clear in your head. This part of elementary vector analysis should be clear in your head. Okay. So, any questions about this? So if you want geometrically, the work done by a force when it moves a body a distance dr, a vector dr, is the length of the force, the distance traveled, times the cosine of the angle between the force and the displacement vector. Okay. I'm almost ready for business, because what is my goal? I find out that in a tiny displacement, f dot dr, I start from somewhere, I go to a neighboring place, a distance dr away. The change in kinetic energy is f dot dr. So let me make a big trip. Okay, let me make a trip in the xy plane made up of a whole bunch of little segments, in each one of which I calculate this, and I add them all up. On the left-hand side, the delta k's, this whole thing was defined so that it's equal to delta k, right? Delta k was equal to this. That's equal to all that. So if you add all the delta k's, it's very clear what you will get. You will get the kinetic energy at the end minus kinetic energy at the beginning. On the right-hand side, you are told to add F dot dr for every tiny segment. Well, that is written symbolically as this. This is the notation we use, calculus. That just means if you want to go from A to B along some path, you chop up the path into tiny pieces. Each tiny segment, if it's small enough to be approximated by a tiny vector dr, then take the dot product of that little dr with the force at that point, which means length of F times the length of the segment times cosine of the angle, add them all up. Then somebody will say, well, your segments are not short enough for me. Well, chop it up some more and chop it up some more, chop it up till your worst critic has been silenced. That's the limit in which you can write the answer as this integral. Just like in calculus, when you integrate a function, you take tiny intervals delta x, multiply f by delta x, but then you make the intervals more and more numerous but less and less wide, and the limit of that is the area under the graph, and that's called integral. You do the same thing now in 2 dimensions. So now maybe it will be true, just like in 1 dimension, that the integral of this function will be something that depends on the endpoint. I'm just going to call it u1 minus u2 of some function u, just like it was in 1 dimension. If that is true, then my job is done, because then I have k1 plus u1 is k2 plus u2. So when I'm looking for the law of conservation of energy, I got to go to some calculus book, and I got to ask the calculus book, look, in 1 dimension, you told me the integral of f from start to end is really the difference on another function g at the end minus the start, where g is that function whose derivative is f. Maybe there is going to be some other magic function u in 2 dimensions related to f in some way, so that this integral is again given by a difference of something there minus something here. If that is the case, then you can rearrange it and get this. But you will find that it's not meant to be that simple. So again, has anybody heard rumors about why it may not be that simple? What could go wrong? Okay, so yes? Okay, that's probably correct, but say it in terms of what we know. What can go wrong? I'm saying in 1D, and I did an integral. Integral was the difference of 2 numbers, right? And therefore, I got k plus u is k plus. So something should go wrong somewhere here. When I say this integral from start to finish is the difference only of the ending point minus the starting point. Is that reasonable, or could you imagine it depending on something else? Yes?
Like, we'll say you have one of your forces is friction. If you take a certain path from point 1 to point 2, it should you should have like the same kinetic and potential energy. But if you take a longer path and there's friction involved, your kinetic energy will be decreased.
Absolutely correct. It's certainly true that if you got friction, this is not going to work. It doesn't even work in 1D. In 1D, if I start here and end here, and I worry about friction, if I went straight from here to here, there's some amount of friction. If I just went back and forth 97 times and then I ended up, there is 97 times more friction. So we agreed that if it's friction, this is not going to work. But the trouble with friction was the force was not a function only of x and y. It depended on the direction of motion. But now I grant you that the force is not a function of velocity. It's only a function of where you are. Can something still be wrong? Well, let me ask you the following question. Another person does this. Do you think that person should do the same amount of work? Because the force is now integrated on a longer path. So you see, in 1 dimension, there's only one way to go from here to there. Just go, right? That's why when you write an integral, you write the lower limit and the upper limit, and you don't say any more, because there's only one way in 1D to go from x1 to x2. In 2 dimensions, there are thousands of ways to go from one point to another point. You can wander all over the place, and you end up here. Therefore, this integral, even if I say the starting point is r1, and the ending point is r2, where this is r1, and that's r2, is not adequate. What do you think I should attach to this integration? What other information should I give? What more should I specify? Yep?
Along a closed path.
No, it's not a closed path. I'm going from 1 to 2. What more should I tell you before you can even find the work done? Yes?
What path you're going on?
You have to say which path you're going in, because if you only have 2 points, 1 and 2, then there is a work done, but it depends on the path. If the work depends on the path, then the answer cannot be a function of u1 minus u2. Cannot just be u1 minus. u1 minus u2 says, tell me where you ended, tell me where you start, and that difference of some function u between those 2 points is the work done. In other words, I'm asking you to think critically about whether this equality really could be true. This is some function u in the xy plane evaluated at one point minus the other point. This is on a path joining those 2 points, but I have not told you which path, and I can draw any path I like with those same endpoints. Now, you've got to realize that it's very unreasonable to expect that no matter which path you take, you will get the same answer. Okay? So you might think that I'm creating a straw man because it's going to turn out by some magic that no matter what force you take, somehow due to the magic of mathematics, the integral will depend only on the endpoints. But that's not the case. In general, that won't happen. So I have to show you that. So I'm going to start by asking you for give me a number from 1 to 3. 2? Okay, 2. Then I want a few more numbers. Another number from 1 to 3? Okay. All right, then 2 more. Mark, you pick a number.
1.
Good, thank you. Then I need 1 more. Yes? 1 to 3. A number from 1 to 3. 2. Very good. Okay, so you pick these numbers randomly. I'm going to take a force which looks like I times x squared y cubed plus j times x y squared. Okay? I put the powers based on what you guys gave me. So we pick the force in 2 dimensions out of a hat. Now let's ask, is it true for this force that the work done in going from one point to another depends only on the path? Or does it depend, depends only on the endpoints, or does it depend in detail on how you go from the endpoints? You all have to understand before you copy anything down where we are going with this. What's the game plan? So let me tell you one more time, because you can copy this all you want. It will get you nowhere. You should feel that you know where I'm going, but the details remain to be shown. But you should have an idea what's happening. If you try to generalize the work energy theorem to 2 dimensions, this is what happened so far. You found a definition of work which has the property that the work done is the change in kinetic energy. Then you added up all the changes in kinetic energy and added up all the work done, and you said k2 minus k1 is integral of f dot dr. That's guaranteed to be true. That's just based on Newton's laws. What is tricky is the second equality, that integral is the difference in a function calculated at one endpoint minus the other endpoint. If that was true, if the integral depended only on the endpoints, then it cannot depend on the path that you take. If it depends on the path, every path you take between the same 2 endpoints will give different numbers, so the answer cannot simply be u1 minus u2. First, I'm trying to convince you through an example that I selected randomly that if you took a random force and found the work done along one path or another path, you will in fact get 2 different answers. Okay? That's the first thing, to appreciate that there's a problem. So generally, if you took a random force, not a frictional force, the force depends only on location, not velocity, it will not be possible to define a potential energy, nor will it be possible to define a k plus u so that it doesn't change. So it's going to take a very special force for which the answer depends only on the starting and ending point and not on the path. To show you that that's a special situation, I'm taking a generic situation, namely a force manufactured by this class without any prior consultation with me, and I will show you that for that force, the answer is going to depend on how you go. So let's take that force, and let's find the work done in going from the origin to the point 1, 1. So I'm going to take two paths. One path, I'm going to go horizontally till I'm below the point, then I'm going straight up. Okay? So let's find the work done when I go this way. So you should be thinking all the time. You should say, if this guy got struck by lightning, can I do anything? Or am I just going to say, well, I don't know what he was planning to do. You've got to have some idea what I'm going to do. I'm going to integrate f dot dr, first on the horizontal segment, then on the vertical segment. F is some vector. You give me at the point x and y, I'll plug in some numbers. I'll get something times I times something times j. It may be pointing like that at this point. That's f. That's given. But now when I'm moving horizontally, my displacement dr has only got a dx part. I hope you see that. Every step I move, there's no dy in it. It's all horizontal. So f dot dr just becomes fx dx, because there is no dy when you move horizontally. So when you do the integral, you have fx dx. Fx happens to be x squared y cubed dx, x going from 0 to 1. Now what do I do with y cubed? You all know how to integrate a function of x times dx. What do I do with y cubed? What do you think it means? Pardon me? What should I do with y? You evaluate y on that path at that point. Well, it turns out throughout this horizontal segment, y is 0. So this is gone. Basically, the point is very simple. When you move horizontally, you're working against the horizontal force is doing work. But on the x-axis, when y is 0, there is no horizontal force. That's why there's nothing to do. Now, if you come to this segment, I think you all agree the distance traveled is j times dy. So I have to have another segment, the second part of my trip, which is fy times dy, and y goes from 0 to 1. And the y component is x y squared dy, where y goes from 0 to 1. But now, on the entire line that I'm moving up and down, x is equal to 1. Do you see that? X is a constant on that line. So you can replace x by 1, and y squared dy is y cubed over 3, and the work done is therefore 1/3 joules. So the work done in going first to the right and then to the top is 1/3. You can also go straight up and then horizontally by a similar trick. I won't do that now, but because I want to show you something else that's useful for you. I'm going to pick another path which is not just made up of x and y segments. Then it's very easy to do this. So I'm going to pick another way to go from 0, 0 to 1, 1, which is on this curve. This is the curve y equal to x squared. First of all, you've got to understand the curve y equal to x squared goes through the 2 points I'm interested in. Okay, if you took y equal to 5x squared, it doesn't work. But this guy goes through 0, 0 and goes through 1, 1. And I'm asking you, if I did the work done by the force along that segment, what is the integral of f dot dr? So let's take a tiny portion of that. Looks like this, right? That's dr. It's got a dx and it's got a dy. Now, you notice that as this segment becomes very small, dy over dx is the slope. Therefore, dy will be dy divided by dx times dx. In other words, dx and dy are not independent if you're moving in a particular direction. I hope you understand that. You want to follow a certain curve. If you step to the right by some amount, you got to step vertically by a certain amount, so you're moving on that curve. That's why when you calculate the work done, dx and dy are not independent. So what you really want is fx dx plus fy dy, but for dy I'm going to use dy dx times dx. In other words, every segment delta y that you have is related to the delta x you took horizontally so that you stay on that curve. So everything depends only on dx. But what am I putting inside the integral? Let's take fx. The x component is x squared y cubed. On this curve, y is equal to x squared. So you really write x squared, and y is equal to x squared, that is x to the sixth. This x cubed is really y cubed written in terms of x. Then I have to write fy, which is x times y squared, which is x to the fourth, times dy dx, which is 2x. So I get here from all of this x to the 8th plus 2x to the 5 dx. Did I make mistakes somewhere? Pardon me? Did I here? Here? Oh, here? Oh, x to the 6th, right. Thank you. How is that? Thanks for watching that. You have to watch it. So now what do I get? X to the 8th integral is x to the 9 over 9. That gives me 1/9 because x is going from 0 to 1. The next thing is x to the 7 over 7, which is 2 times that. Well, I'm not paying too much attention to this because I know it's not 1/3. Okay? There's no way this guy is going to be 1/3. That's all I care about. So I've shown you that if we took a random force, the work done is dependent on the path. For this force, you cannot define a potential energy. Whereas in one dimension, any force that was not friction allowed you to define a potential energy. In higher dimension, you just cannot do that. That's the main point. So if you're looking for a conservative, this is called a conservative force, is a force for which you can define a potential energy. It has the property that the work done in going from A to B, or 1 to 2, is independent of how you got from 1 to 2. And the one force that the class generated pretty much randomly is not a conservative force because the work done was path dependent. So what we have learned, so in fact I'll keep this portion here. If you're looking for a conservative force, a force whose answer does not depend on how you went from start to finish, then you have to somehow dream up some force so that if you did this integral, the answer does not depend on the path. You realize that looks really miraculous because we just wrote down an arbitrary force that we all cooked up together with these exponents, and the answer depends on the path. And I guarantee you, if you just arbitrarily write down some force, it won't work. So maybe there is no law of conservation of energy in more than one dimension. So how am I going to search for a force that will do the job? Are there at least some forces for which this will be true? Yes?
The force is always parallel to the path along which you add.
No, but see, the point is, you got to first write down a force in the xy plane. Then I should be free to pick any 2 points and connect them any way I like, and the answer shouldn't depend on how I connected them. Only then you can have conservation of energy. I hope you all understand that fact. So I'm saying a generic force on the xy plane doesn't do that. Then we ask, can there ever be an answer? It is so demanding. Yes?
What about an inverse square force like gravity?
Right. So he's saying, I know a force, the force of gravity, in fact, happens to have the property that the work done by the force of gravity does not depend on the path. We will see why that is true. But you see, what I want is to ask, is there a machine that will manufacture conservative forces? And I'm going to tell you there is. I will show you a machine that will produce a large number of, infinite number of conservative forces. And I'll show you how to produce them. Here is the trick. The trick is, instead of taking a force and finding if there's a potential that will come from it by doing integrals, let me assume there is a potential. Then I will ask what force I can associate with the potential, and here is the answer. The answer is, step 1, pick any u of x and y. You pick the function first. That function is going to be your potential energy. It's been anointed even before we do anything. But then, from the potential, I want you to manufacture the following force. I want you to find the force that I'm going to find is going to have an x component, which is the derivative of u with respect to x, and it's going to have a y component, which is the derivative of u with respect to y. That is step 2. In fact, the claim now is this force is going to be a conservative force. And in fact, its potential energy associated with it will be the function you started with. So how do I know that? So for example, I'm saying, suppose u equal to xy cubed. Then fx is equal to minus du dx, which is equal to minus y cubed, and fy, which is minus du dy, will be minus 3xy squared. The claim is if you put I times fx and di times fy, the answer will not depend on how you got from start to finish. So let me prove that to you. Here is the proof. The change in the function u in the xy plane, you guys remember my telling you, is du dx times dx plus du dy times dy. That's the old thing of mathematical preliminaries, which was done somewhere. I forgot. Here. It says here delta f is delta f delta x times delta x, delta f delta y times delta y. Apply it to the function u. But who is this? You notice what's going on here? Du dx dx, this is fx with a minus sign. That's fy, the minus sign. Therefore, this is equal to minus f dot dr. Right? Because we agree the force that I want to manufacture is related to u in this fashion. Now, if you add all the changes, the right-hand side becomes the integral of f dot dr, and the left-hand side becomes the sum of all the delta u's with a minus sign. Add all the delta u's with a minus sign, that will just become u at 1 minus u at 2. It is cooked up so that f dot dr is actually the change in the function u. That's the, if you say, what was the trick that you did? I cooked up a force by design so that f dot dr was a change in a certain function u. If I add all the f dot dr's, I'm going to get a change in the function u from start to finish. So it's got to be u1 minus u2. So I don't know how else I can say this. Maybe the way to think about it is, why do certain integrals not depend on how you took the path, right? Let me ask you a different question. Forget about integrals. You are on top of some hilly mountain. We have a starting point, you have an ending point. Okay? I start at the starting point and I walk to the ending point. At every portion of my walk, I keep track of how many feet I'm climbing. That's like my delta u. I add them all up. At the end of the day, the height change will be the top of the mountain minus bottom of the mountain, the height of the mountain. You go on a different path. You don't go straight for the summit. You loop around and you coil and you wind down, you go up, you do this, and you also end up at the summit. If you kept track of how long you walked, it won't be the same as me. But if you also kept track of how many feet you climbed, and you added them all up, what answer will you get? You'll get the same answer I got. Therefore, if what you were keeping track of was the height change in a function, then the sum of all the height changes will be simply the total height change, which is the height at the end minus height at the beginning. Therefore, starting with the height function, by taking its derivatives, if you manufacture a force, this will be none other than the fact of adding up the changes. Okay, and that's why this will be k2 minus k1, and then you will get k1 plus u1 is k2 plus u2. So I hope you understand how conservative forces are not impossible to get. In fact, for every function u of x and y you can think of, you can manufacture a conservative force. So you may ask following question. Maybe there are other ways to manufacture a conservative force, and you just thought of one. And the answer is no. Not only is this a machine that generates conservative forces, my two-step algorithm, pick a u and take its derivatives, every conservative force you get is necessarily obtained by taking derivatives with respect to x and y of some function u. And that u will be the potential energy associated with that force. So that when that force alone acts on a body, then kinetic plus that potential will not change. Finally, you remember that when the class picked a certain force, which I wrote here, I went on a limb and I said, I'm going to do the integral of this force along this path and that path, and I'm going to get different answers and show you we have a problem. What if the force you had given me was actually a conservative force? Then I would be embarrassed, because then I will find, after all the work, this will turn out to be again 1/3. So I had to make sure right away that the force is not conservative. And how can you tell? One way to say it is ask yourself, could that be some function u whose x derivative of this was this and whose y derivative was that? You can probably convince yourself no function is going to do it for you. Because if you took an x derivative, you should have lost a power of x here. That means if you just took the y derivative to go here, you should have more powers of x and less powers of y, but this is just the opposite way. So we know this couldn't have come from a u. But that's a better test instead of doing all that. Instead of saying, I'm satisfied that this doesn't come from taking derivatives of a u by looking at possible u's and not being satisfied because maybe I'm not clever enough. There is a mechanical way to tell. Mechanical way to tell is the following. Maybe I want you guys to think for a second about what the recipe may be. If a force came from a function u by taking derivatives as written up there, what can you say about the components of that force? From the fact, yes? Right, so we know that for every function u, the cross derivatives are equal. But the ordinary derivatives are just the fx and fy. Therefore, d2u over dy dx is really d by dy of fx. And I want that to be equal to d by dx of fy, because that would then be d2u over dx dy. In other words, if the force satisfies this condition, the y derivative of fx is the x derivative of fy, then it has the right pedigree to be a conservative force. Because if a force came from a function u by taking derivatives, the simple requirement that the cross derivatives are equal for any function u tells me, see, if I take the y derivative of fx, I'm taking d2u dx dy. And here I'm taking d2u dx dy dx, and they must be equal. So that's a diagnostic. If I give you a force and I ask you, is it conservative, you simply take the y derivative of fx and the x derivative of fy, and if they match, you know it's conservative. So I got to summarize by saying the following thing. In 2 dimensions, there are indeed many, many forces for which a potential energy can be defined. But every one of them has an ancestor, which is simply a function, not a vector, but a scalar function, an ordinary function of x and y. Then the force is obtained by taking x and y derivatives of that function. The x derivative with a minus sign is called fx, and the y derivative is called fy. Okay, so let's take the most popular example is the force of gravity near the surface of the earth. The force of gravity, we know, is minus mg times j. Is this guy conservative? Yes, because the x derivative of this vanishes, and the y derivative of fx you don't even have to worry because there is no fx. So it's clearly conservative. Then you can ask, what is the potential u that led to this? Well, du dy with a minus sign had to be minus mg, and du dx had to be 0. So the function that will do the job is mgy. You can also have mgy plus 96, but we will not add those constants because in the end, in the law of conservation of energy, k1 plus u1 is k2 plus u2. Adding a 96 to both sides doesn't do anything. So this means when a body is moving in the gravitational field, 1/2 mv square plus mgy before is the same as 1/2 mv square plus mgy after. Now, you knew this already when you're moving up and down the y direction. But what I'm telling you is this is true in 2 dimensions. So I'll give you a final example so you guys can go home and think about it. That is a roller coaster. So here's the roller coaster. It has a track that looks like this. This is x. This is the height of the roller coaster. But at every x, that's a certain height, so y is a function of x. And it looks like this. It's just the profile of the roller coaster. But that is also the potential energy u, because if you multiply this by mg, well, you just scale the graph by mg, it looks the same. So take a photograph of a roller coaster, multiply the height in meters by mg, it's going to still look like the roller coaster. That is my potential energy for this problem. And the claim is that kinetic plus potential will not change. So k plus u is a constant. Let's call the constant E. So if a trolley begins here at the top, what is its total energy? It's got potential energy equal to the height. It's got no kinetic energy. The total energy, in fact, is just this height. And total energy cannot change as the trolley goes up and down. So you draw a line at that height and call it the total energy. You started this guy off with that energy. That energy must always be the same. What that means is if you're somewhere here, since that is your potential energy, that is your kinetic energy. It's very nicely read off from this graph to reach the same total. So as you oscillate up and down, you gain and lose kinetic and potential. When you come here, your potential energy is almost your whole energy, but you got a little bit of kinetic energy. That means your roller coaster is still moving when it comes here with the remaining kinetic energy. You can have a roller coaster whose energy is like this. Is it released from rest here? If it's released from rest here, that's the total energy, and its total energy line looks like this. That means if you released it here, it'll come down, pick up speed, slow down, pick up speed again, and come to this point, it must stop and turn around. Because at that point, the potential energy is equal to total energy, and there's no kinetic energy. That means you stopped. That means you're turning around. It'll rattle back and forth. By the way, according to the laws of quantum mechanics, it can do something else. Maybe you guys know. You know what else it can do if it starts here? Yes? It can suddenly find itself here. And that's not allowed by classical mechanics, because to do that, it has to go over the hump. Look what's happening at the hump. I got more kinetic energy than I have total energy. I'm sorry, I got more potential energy than I have total energy. That means kinetic energy is negative. That's not possible, because 1/2 mv squared can never be negative. So quantum theory allows those forbidden processes, and it's called tunneling. But for us, the roller coaster problem, you will just turn around. There's one thing I want you to think about before you go. You should not have simply accepted the law of conservation of energy in this problem, because gravity is not the only force acting on this. What else is acting on this roller coaster? Pardon me? No friction. Then what? The force of the track. Look, if I didn't want to have anything but gravity, here's a roller coaster ride you guys will love. Just push you over the edge. Okay? That conserves energy, and it's got no track. And it's got the only gravitational force, and you can happily use this formula. Why am I paying all this money? Because there's another force acting on it. But that force, if it's not frictional, is necessarily perpendicular to the motion of the trolley. And the displacement of the trolley is along the track, so F dot dr vanishes. So I will conclude by telling you the correct thing to do would be to say K2 minus K1 is the integral of all the forces divided into force due to the track and the force due to gravity. Force due to the track is 0. I mean, it's not 0, but that with the dot product with dr is 0, because F and dr are perpendicular. For that reason, you drop that. And the force of gravity is cooked up so that it becomes u1 minus u2, and that's what we used. Okay, one challenge, you guys can go home and do this. Take any force in 2 dimensions, F. It is parallel to the direction where you are, measured from the origin, times any function of the distance from the origin. Convince yourself that this force is a conservative force by applying the test I gave you. And the trick is to use x and y instead of r. Take this force, write it out in terms of x and y, take the cross derivatives, and you can see it's conservative. So any radial force, yep. Oh, here, this is the force to which you should try your thing. And gravity is a special example of this. Okay, judging from the class reaction and the stunned and shocked look, a lot of you people, maybe this material is new, so you should think about it, talk about it, go to discussion section. But this is the level at which you should understand energy conservation in a course like this.